Are we alone in the universe? Or is there intelligent life out there that we've yet to discover? Could advanced civilizations be hiding from us? Or are they preparing to launch an attack? And what if the key to unlocking the secrets of the universe lies in the existence of silicon-based life? Join us on a journey through space and time as we explore these questions. From the possibilities and challenges of interstellar travel to the paradoxes that confound our understanding of the cosmos. This video will take you on an unforgettable adventure into the unknown. Are you ready to discover what lies beyond the stars? The dream of exploring the depths of space beyond our solar system has long captured the imagination of mankind. But is interstellar travel just a distant fantasy, or can we really achieve this goal in the near future? Thanks to the scientific and technological advances made in recent years, we're closer than ever to interstellar travel becoming a reality. The development of new propulsion systems, advances in material science, and our understanding of cosmological theories brings us closer to developing the necessary infrastructure and technology for interstellar missions. However, this ambitious goal has its challenges. The vast distances between stars and the large number of threats lurking in outer space make interstellar travel difficult and potentially dangerous. If we're being optimistic, and certainly not unrealistic, humans will be able to achieve interstellar travel within our lifetime. The possibilities are endless, and the rewards could be extraordinary. The difficult task of interstellar travel is primarily defined by the vast expanses between stars. Our closest neighbor, Proxima Centauri, is a little over 4.2 light years away. This means that even if we traveled at the maximum speed currently possible in the universe, which is the speed of light, the journey would take more than 4 years. Despite contemporary advancements in technology, achieving these speeds is still impossible. Even with the most advanced propulsion technology currently available, such as nuclear or ion propulsion, it would take a spacecraft decades, if not centuries, to reach the nearest stars. To overcome this problem, the best option is to develop new engine technologies that can achieve much greater speeds. Various concepts on how to achieve that are being considered, including the idea of using antimatter, thermonuclear fusion, or even harnessing the forces of black holes. Nuclear fusion, the process that powers the sun and other stars, involves combining two light atomic nuclei, such as hydrogen, to form a heavier nucleus and release the energy. Although nuclear fusion technology is still in its infancy on Earth, it has the potential to provide an almost limitless source of energy and could be used to power spacecraft engines. However, these feats of technology are still purely theoretical, and there is no telling whether they will ever be possible in practice or safe enough to use. The complexity of interstellar travel as a concept is exacerbated by the astronomical amount of fuel and energy required to travel such great distances. The traditional rocket propulsion technology relies on huge amounts of fuel propelling spacecraft at a speed only a fraction of the speed of light. For instance, the Parker Solar Probe is the fastest traveling spacecraft ever built by humans, and can only reach the speed of 119.4 miles per second. For reference, this is only 0.064% of the speed of light. In order for us to reach Alpha Centauri in human lifetime or less, we need to figure out how to develop a speed of at least 10% of the speed of light. However, the paradoxical nature of this task is that in order to increase the speed of the spacecraft, we need more fuel. By carrying more fuel on board the ship, the weight of the vessel increases, which subsequently reduces its speed. Sounds like a vicious circle. Nuclear or ion propulsion engines are the most advanced propulsion technology that's currently available. Offering much greater efficiency in terms of fuel consumption, they still require a significant amount of fuel to generate the required power. To overcome these obstacles, researchers are developing completely new propulsion technologies that could harness the energy sources available in space. For instance, scientists are exploring the possibility of using solar sails, which use the energy coming from the sun, similar to the way regular sails use the wind to ensure the continuous acceleration of the spacecraft. Another solution that's been put forward is to use antimatter propulsion, which would allow the spacecraft to achieve much greater speeds while consuming less fuel. Antimatter is a unique substance that has the same mass as regular matter, but with the opposite electric charge. When matter and antimatter come into contact, they annihilate each other, releasing tremendous amounts of energy. Antimatter is capable of delivering much denser energy than any technology currently available. Theoretical calculations suggest that a spacecraft functioning on antimatter could potentially reach up to 90% of the speed of light. This would mean it could reach Proxima Centauri in just over 4 years. Scientists have been conducting experiments with antimatter for decades. One of the earliest experiments involved creating antiprotons, which are the antimatter equivalent of protona. The first antiprotons were generated in 1955 by a group of scientists at the Lawrence Berkeley National Laboratory in California. However, antimatter is very costly and difficult to produce, and the technology to use it for propulsion is still at an experimental stage. Furthermore, antimatter is highly unstable and difficult to store. Its particles cannot be stored in a traditional container, as they would quickly come into contact with matter and destroy each other. Instead, magnetic fields were developed specifically for the task of capturing and storing antimatter. To sum up, the need for large amounts of fuel and energy for interstellar travel poses enormous challenges for the progress. However, developing a completely new propulsion technology or harnessing energy from sources available in space is definitely a necessary push in the right direction. Once we find a way to travel fast enough, we still won't be ready for interstellar travel, since even Columbus did not travel blindly in his search for a new route to India. Navigation and communication during interstellar travel present another major challenge for manned missions. The great distances between stars means that there could be significant delays in communication with Earth. This would make real-time communication difficult or even impossible. Furthermore, signals from Earth could be faced with interference, noise, or they could become completely lost, making data acquisition and interpretation very difficult. To resolve these issues, spacecraft will require advanced communication and navigation systems capable of handling the unique demand of interstellar travel. One possible way to do that is to use a network of interstellar satellites that could relay information between Earth and the ship, ensuring faster and more reliable communications. Another promising solution is quantum communications technology, which uses entangled quantum particles to transmit information instantaneously over long distances. This technology could revolutionize interstellar communications by allowing real-time transmission of data without any delay or interference. Another option is to use advanced artificial intelligence that could help spacecraft navigate the vast expanses between stars and adjust course as needed, even without any involvement of a human controller. Accurate navigation is key for successful interstellar travel. Even the slightest deviation can throw a spacecraft off course for millions of miles. To minimize the risk of this happening, the ships will need incredibly accurate navigation systems, such as ones using pulsars as reference points. Pulsars are highly magnetized, rotating neutron stars that emit beams of electromagnetic radiation from their poles. Think of them like cosmic beacons. As the pulsar rotates, it sends out the beam of radiation that shoots through space, creating a so-called momentum. Pulsars are incredibly reliable and predictable, making them ideal candidates for deep space navigation. For example, the technology of gravity assist trajectory used on the New Horizons spacecraft mission to Pluto relied on Jupiter's gravitational forces to guide the spacecraft to its target. However, as with any complex system, there is always a risk of hardware malfunctioning in some way. Without human intervention in real time, these failures can have catastrophic consequences, potentially leading to the loss of the crew and the mission as a whole. That is why, in the absence of accurate and reliable communication and navigation systems, a mission to the nearest stars would not have any success. But no matter how highly equipped the ship is, as it rushes towards distant stars, the most important component of the mission are still the people on board. The most important task in interstellar travel is to provide the crew with sufficient resources to survive during the journey. This includes developing life support systems that could provide enough food, water, and oxygen. With current technology, it is only possible to store a limited amount of resources, not enough for truly long journeys. Therefore, we need new technologies and ways to sustain life while traveling over a long distance. One potential solution is to develop regenerative life support systems that can recycle waste and convert it into useful resources. Additionally, the development of advanced food growing and oxygen producing systems aboard spacecraft is a must in research. Another option is to put astronauts into deep sleep for the duration of their journey, similar to the way animals hibernate in winter. Scientists are exploring the use of this technique known as suspended animation or hibernation, although at the moment it presents significant medical challenges as to how to keep the crew in this suspended state for long periods of time without causing serious health issues, which could significantly reduce the resources and life support systems required. Moreover, prolonged exposure to zero gravity can have detrimental effects on the human body. Leads to muscle atrophy, loss of bone density, and other physical changes. Therefore, to maintain the health of the crew during the journey, physical exercise and medical intervention may be required. To counteract the negative effects of zero gravity, what may help is an artificial gravity system in place. One way to do that is to maintain the constant rotation of the spacecraft. The centrifugal force created by rotation can mimic the gravitational force that we experience on Earth. This approach has been researched and successfully tested on various space missions, including Skylab and the International Space Station. Another major health concern when it comes to interstellar travel is radiation. Space is riddled with an endless array of radioactive emissions, long-term exposure to which poses a significant health risk to astronauts. Outside of Earth's protective magnetic field, humans are exposed to high levels of ionizing radiation, including cosmic rays and solar flares. Radiation causes damage to human cells, leading to various health problems, including cancer and other illnesses. Additionally, exposure to cosmic radiation can cause genetic damage to DNA that can be passed to future generations. To reduce the risk associated with radiation exposure, interstellar spacecraft must be designed in a way that shields the crew. This shield must be strong enough to block harmful radiation while at the same time being light enough to not significantly increase the weight of the spacecraft. It must be adapted to all types of radiation that the spacecraft may encounter during its journey. To address these issues, researchers are exploring various options for protection against radiation, including the use of artificial magnetic fields, as well as advanced technologies and specialty materials. In addition, the crew may need to take special medications or undergo medical procedures to reduce the effects of radiation sickness. In addition to the tiniest radiation particles, another danger you may encounter during interstellar travel are debris and asteroids. Asteroids and comets pose a threat to the spacecraft because they're difficult to detect and avoid. Space debris can cause significant damage to the ship, and even a small item moving at a high speed can cause catastrophic damage to a vessel. To ensure the safety of astronauts and the spacecraft itself, some form of protection is required. Shielding of the spacecraft from danger can be achieved through a variety of methods, including building thick walls and using material that would absorb or deflect radiation and debris. Additionally, the spacecraft could be equipped with sensors and detection systems to help identify potential hazards and avoid them. However, we're once again faced with the fact that the materials needed for effective protection are rather heavy. Although security technologies and detection systems have advanced significantly in recent years, further research and development is required to overcome these obstacles and ensure the safety of astronauts and spacecraft. Either way, interstellar travel is an ambitious goal that will require significant investment and resources from governments and private entities around the world. The cost of interstellar travel will include research and development of new propulsion systems, life support systems, navigation and communications technology, protection from radiation and interstellar hazards, and more. The cost of developing the necessary infrastructure and technologies is likely to be prohibitive and will require significant cooperation and commitment from the global community. It's also possible that conflict of interest or opposing investor agendas could cause controversy and impede progress, which could ultimately limit the scope of interstellar research and development. One possible solution to offset the cost of interstellar travel could be the development of space mining technology. Space mining involves extracting valuable resources from asteroids and other celestial bodies that could potentially provide funding for interstellar missions. Furthermore, advances in space manufacturing and 3D printing could make it possible to create spacecraft and other materials directly in outer space, reducing the cost of launching them from Earth. Without a long-term commitment to developing the necessary infrastructure, technologies, and resources, interstellar travel may remain out of reach for humankind. Conceptually, a completely different approach to interstellar travel is the construction of a generation ship. A generation ship is a hypothetical spacecraft for interstellar travel, requiring an indefinite number of generations before they reach their final destination. Instead of trying to reach a destination within the lifetime of the initial crew, these spaceships would carry generations of passengers who are born and live their entire lives on the spacecraft. The generation spacecraft concept has been proposed as a potential solution to some of the challenges of interstellar travel, including significant distances and the limitations of current propulsion technology. By allowing multiple generations of passengers to be born and raised during the journey, one can envision a scenario in which the crew can maintain the necessary resources and technology to complete the mission, even if it takes an extremely long time. However, this concept is not without its flaws. We must resolve the issues of recruiting and managing crew, allocating resources, and maintaining social cohesion over long periods of time. Moreover, there's a possibility that the knowledge and technology needed for the mission may degrade or be lost over time, which could jeopardize the success of the mission. Despite these issues, the concept of generation spacecraft remains a popular topic in science fiction and theoretical discussions about interstellar travel. To sum everything up, let's recall the classic walk-wait dilemma, which is a common predicament in decision-making. It occurs when a person must make a choice between expecting a more desirable outcome or taking immediate action to to achieve a less desirable but still acceptable outcome. For instance, it may occur when you're waiting at a bus stop, but the waiting time may exceed the time required to arrive at the destination in another way, such as on foot. This scenario can be applied to interstellar travel, presenting us with a dilemma of whether we should launch interstellar ships now or wait for technologies that will generate greater speed and allow new ships to reach destinations faster. The ethical dilemma here is whether it would be fair to the crew of the first ships to make a senseless sacrifice in case the rate of technological advancement suddenly surpassed that of the first ships. Put yourself in the shoes of a pioneering crew member in another star system. You've spent decades or even centuries in space wondering if newer and faster ships may have arrived at your destination long before you. This dilemma raises deep questions about the value of human life, the responsibility for space exploration, and the importance of progress. Waiting for new technologies could lead to faster, more efficient travel, but it could also mean that the first crew would suffer or be exposed to dangers that future generations may not even have to face. Conversely, launching ships now can be seen as unfair to the crew, as they will not benefit from the same advanced technology that future generations will. Ultimately, the final decision will depend on how society perceives the importance of progress and research in relation to the value of human life. In a quest to understand the vast and mysterious universe, science has long mastered the powerful tool of logic. But even when using the most rigorous methods and the most advanced technologies, paradoxes inevitably arise, contradictions that challenge our understanding of the world. One such paradox is the dark sky at night. How is it possible that we're surrounded by an infinite number of shining stars, and yet the sky remains dark? The other is the nature of dark matter, an elusive substance that escapes the grasp of even the most advanced instruments. And what about the inevitability of oblivion? The solar system, along with our planet and ourselves, may eventually disappear into oblivion, forever lost in the vastness of time and space. These paradoxes are not just philosophical ruminations. They have real implications for our understanding of the universe. They force us to reconsider our assumptions and question the things we think we're sure of. They encourage us to go beyond our current understanding and delve deeper into the mysteries of the cosmos. And in the end, faced with these paradoxes, we can gain new understanding and move forward in our comprehension of the universe. The Horizon Problem. The horizon paradox, also known as the horizon problem, is a paradox arising from the observations that the temperature of the cosmic microwave background radiation, or CMB, is practically uniform throughout space, despite the fact that regions of the universe separated by vast distances have not had enough time to reach thermal equilibrium. The root cause of the horizon problem is that the CMB is a remnant of the time the universe was in a hot and dense state known as the Big Bang. The CMB is the almost perfect blackbody radiation, characterized by the uniform temperature of approximately 2.7 Kelvin in all directions. However, if the universe continued to expand, in about 13.8 billion years, certain regions of the universe separated by such vast distances would not have time to reach thermal equilibrium and therefore be of the same temperature. This paradox suggests that the temperature of the CMB does not have to be the same throughout the universe. The horizon problem has baffled cosmologists for decades and prompted a number of proposed solutions. One solution is the theory of cosmic inflation, which states that the universe underwent a rapid expansion in the early stages of its formation. This expansion would have smoothed out any initial fluctuations in temperature, making the temperature of the CMB about the same throughout the universe. Inflation models also explain the homogeneity and isotropy of the universe, two more major observational mysteries in cosmology. Another possible answer is the concept of causality. Causality is a fundamental principle in the sciences. It's the idea that every occurrence, action, or event is preceded by a cause that determines its effect. The idea is that the early universe was in equilibrium and was much denser and hotter. Photons of relic radiation in this state of the universe were in casual contact. That meant they could interact with each other and achieve thermal equilibrium. The third solution is the concept of cosmic variance. The gist of this idea is that the universe is much larger than we can observe, and temperature fluctuations are simply statistical deviations from the average temperature of the universe. In general, the horizon paradox is a complex and multidimensional problem that has not yet been fully resolved. Each of the proposed solutions has its own strengths and weaknesses, and a true resolution of the paradox may require a combination of these ideas or even an entirely new theory. Olber's paradox. Olber's paradox, also known as the redshift paradox, is a mystery that's puzzled astronomers for centuries, named after the pioneering German astronomer Heinrich Olbers. This paradox arises from the contradiction between the presumably infinite number of stars in the universe and the darkness of the night sky. The gist of the paradox lies in the fact that if the universe were truly infinite and eternal, and the stars were evenly distributed throughout the endless bounds of outer space, then in any direction we looked, we would see a star. The light from these stars, however distant, would eventually reach our planet. Therefore, the night sky should be illuminated with the same intensity as the surface of the sun. However, despite this logical reasoning, the night sky remains dark, presenting a perplexing enigma for scientists and stargazers alike. Several possible solutions have been put forward to explain this mystery. One solution is that the universe is not uniform and isotropic, meaning that the stars are not evenly distributed throughout space. This could be due to the presence of large-scale structures such as galaxy clusters and voids that would create dark patches in the night sky. In addition, light from the more distant stars could be absorbed by intergalactic dust, making the night sky appear darker. This theory is supported by observations of major redshifts in distant quasars. Another possible solution lies in the expansion of the universe. The farther back we look, the further away the light sources would be from us. When we look back into the past, the universe becomes denser, more hotter and brighter. As a result, the light from distant stars is shifted to the red end of the spectrum and therefore become too faint to be seen. We can't say for sure whether our universe is infinite, but according to the Big Bang Theory, we know one thing for sure: our universe has a beginning. Additionally, the assumption that the universe is a finite would mean that the light from distant stars does not reach us simply because our universe is constantly expanding. Because of this, the wavelength of the light from distant stars is greatly stretched, and it eventually reaches Earth in the infrared range. It would also mean that the light from distant stars has either not yet managed to reach us, or the stars have already died out. On the other hand, if we assume that our universe is infinite, then it's quite natural that at some point, due to the constant expansion of the universe, stars and matter would begin to acquire a speed that exceeds the speed of light. This would make it impossible for light to reach Earth. The enigma of the Olbers paradox remains one of the most intriguing mysteries in cosmology, and its solution requires a deeper understanding of the nature and structure of our universe. The flatness problem. The flatness problem is a paradox that arises from the observation that the universe is almost perfectly flat, despite the fact that the density of its matter is far from sufficient to maintain such a state, which begs the question, why is the universe flat? And what do we mean when we classify it as such? The flatness of the universe means that space-time is not curved and the amount of matter and energy is just right for the universe to be flat. However, the density of matter and gravitational energy in the universe are much lower than necessary, which should cause it to either expand too quickly or collapse. And this, of course, makes us wonder, how does the universe maintain its flat shape? In a nutshell, that's the essential principle of the flatness problem, a mystery that continues to haunt some of the greatest minds in the field. There are several possible solutions to the flatness paradox. One potential solution is the elusive concept of dark energy. It is believed this mysterious form of energy contributes to the acceleration of the expansion of the universe. Dark energy is believed to contribute 68% of the total energy in the present-day observable universe. It has negative pressure and acts as a repulsive force, counteracting the gravitational force of matter and causing the universe to expand at an accelerated rate. This acceleration would help to flatten the universe. Another solution is the concept of inflation. According to the theory of inflation, the universe underwent a rapid expansion in the early stages of its formation. As space expands, the geometry of space becomes flatter. To help you understand, imagine a balloon. As it fills with air and inflates, its surface becomes smoother and flatter. This type of expansion would smooth out any initial density changes, making the universe nearly flat. The third solution is the multiverse theory, which suggests that our universe is just one of many. According to this theory, there are a large number of universes, and based on this, the likelihood that one of them will be flat is much higher than if there was only one universe. The monopole paradox. The monopole paradox is yet another example of an unyielding mystery of the universe. This is a paradox that comes from the observation that there are no observable magnetic monopoles, despite the fact that their existence is predicted by several theories of particle physics and should be present in the universe. Magnetic monopoles are hypothetical particles with a single magnetic pole, while all known magnets have a north and south pole. The existence of these hypothetical particles has been predicted in theories such as the Grand Unified Theory, a Grand Unified Theory or GUT, and quantum gravity theories. However, despite great efforts and extensive research, no magnetic monopoles have been found. Nonetheless, despite their elusive nature, there are many theories attempting to explain their apparent absence. One possible explanation for the absence of magnetic monopoles is their instability that causes them to decay into other particles, making them undetectable in the modern universe. Another theory claims that magnetic monopoles were created during a supersymmetry transition in the early universe, but they're now too rare for us to be able to observe them. The idea is that in the early universe, the symmetry of the laws of physics was different than it is now, and these symmetries were broken during a phase transition, similar to how water changes from a liquid to a solid when it freezes. During this phase transition, magnetic monopoles should have appeared as a result of breaking symmetry. However, as the universe has expanded and cooled, these monopoles have diluted and are now too rare to be observed. The search for these hypothetical particles continues, as does the scientific work with a goal to unravel the monopole paradox and deepen our understanding of the universe. The entropy paradox. The entropy paradox is a paradox that arises from the observation that the universe is ordered and structured. despite the fact that the second law of thermodynamics states that entropy, or in other words disorder, must increase over time. But what does entropy actually mean? We usually talk about it as if it were a measure of disorder, a quantitative representation of the randomness and chaos that exist within a system. A broken egg on the floor has more entropy than an intact egg on the countertop. A spoonful of cold cream and a cup of hot coffee have less entropy than the combination of both stirred together. A chaotic pile of clothing has a higher entropy than a neat set of drawers where all the clothes are folded and organized. According to the second law of thermodynamics, the total entropy of an isolated system will always increase over time. The law implies that the universe should become less ordered as time goes by. However, the very structure of the universe contradicts this idea. We observe that the universe is highly ordered and structured. It contains galaxies, stars, planets, and even life forms. There are several theories that offer possible solutions to this paradox. Each of these solutions offers a different perspective on how the order and structure observed in our universe can be reconciled with the second law of thermodynamics. One solution is the concept of entropy as an arrow of time. The arrow of time is the idea that time has a direction moving from the past and into the future. This concept suggests that while entropy would increase in a closed system